All right, so welcome to Math 119-312. It's nice to meet some of you. Eventually there will be a class, but I'm not so hectic beforehand, and I will get a chance to get to know you a little bit better. This class is actually not the lecture I was going to give maybe 12 hours ago. But based on what happened at the regional school committee last night where I served, I have changed the lecture because there is now a time-sensitive issue. There's an opportunity for you to contribute to state policy. And so I believe the mathematics can be done better than it is being done. This is being recorded, so I will be very careful in the words that I use. I am happy to talk further when this is not a live class being recorded. I believe you all already have enough knowledge to be able to help us solve a problem that is extremely important. This is not a problem where you need 300, 400 level math, where you need graduate level mathematics. You need to look at the right statistic. And so the problem is, what is the right statistic to look at? That is an extremely hard problem. And so what I want to do today is talk about how do we choose among a bunch of different metrics, which is the right one. And the application is to help the Commonwealth of Massachusetts come up with a good way to help advise school districts on whether or not they should be in person, hybrid, or remote. Right now, we are using a color-coded system, and you can see, if you look at the Commonwealth of Massachusetts, a lot of gray areas. So towns with very small populations are often gray. Then a couple of yellows, a couple of greens. So green is the lowest, then yellow, and then red. And I want to talk a little bit about how the state chooses these colors and are they choosing them right. When you look at this map, does anything in Western Mass strike you as interesting? Yes. Williamstown is yellow. We are the highest level in this region. And so I'm not going to talk right now why we are the highest in the region, but I want to be thinking about this in the background as we go through the metrics. You know, should you all be terrified right now and running from this classroom and protecting yourself? Or maybe some of these metrics are not really measuring what we think they're measuring. Right. So what does it mean for a metric or statistic to be good? Can someone give me an idea of what you would like a good statistic to do? Yes?
To be an accurate representation of what you're trying to find.
Beautiful. Please email me that so we can put this in the letter to the state. Well, actually, this is being recorded. So say that again loudly. To be an accurate measurement of what we're trying to find. Does anybody know what an IQ test measures? It measures your IQ. Anybody know what an ideal gas is? It's a gas that satisfies the ideal gas law. You want to be very careful about what you're looking at. And so for a metric or statistic to be good, we want it to be an accurate measurement of what we're trying to describe. So there's a wonderful game. If we have some time at the end of today's class, we will play it. If not, it's on the slide, where each turn you choose either left or right. The computer tries to predict your choice. And if the computer successfully predicts, the computer gets a point, otherwise you do. First to 25 wins. You only have 3 seconds for each turn. You can bank some of your time for future moves, but you can't bank more than 10 seconds. And the question is, who do you think is going to win, you or the computer? The computer. Why? So we will have natural patterns. You may think that you are being random, but if you are a little bit deterministic, the computer might be able to detect that. And it doesn't have to win by much. It only has to beat you a little bit of the time. And if the computer has no idea what you're doing and just guesses randomly, it still has a 50-50 chance. So this is a great example of a small change, a small benefit to the computer is enough to give it a huge increase in probability of beating you. I do know a way to beat the computer. And I will share that. That one does use advanced mathematics. But there are ways to act more randomly. People often do not have a good sense of random. I know somebody who tested positive for COVID on this campus, and they thought it was a false positive. And they were assured, no, 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 no. It's almost surely an accurate test. The probability of being a false positive is very small. Now, this is one of my best students who has done a lot of statistics. What do you think my student said? Yes? Giving so many tests. In fact, a lot of us were wondering, is the Broad Institute actually doing the tests or just collecting our money? For the record, we always thought you were doing the test. We hadn't gotten any positives at first at Williams. And with the number of tests going on, the more tests you have, the more likely it is that there's at least 1 or 2 false positives. And so we will talk more about that later. So you want to be very careful as to how much does a small change affect things. So statistics that are very sensitive to having things exactly measured are not necessarily as good as ones that are a little bit more robust, where you can have a little bit of wiggle room. One of my former students has actually testified before Congress on climate models. And one of the big points he raises is a lot of these models are extremely sensitive to choices of parameters when you're trying to predict what happens. And so depending on what you choose for some of these values, you can change them by just a little bit and have wildly different behavior. So I want you to be aware of stuff like this. Okay. So another opportunity for this class, and again, this is probably the most broadly structured class you will take either in your stay at Williams or when you come back as an alum. Almost anything I will accept as good work. There are a lot of students now who are doing learning from home who are looking for enrichment, for supplement, and stuff like that. Not surprisingly, as a math professor, my kids were not going to fall behind in math last year when we went remote. And I started doing some enrichment lectures for them. And I've done some of these in other places all around the world. I have several good friends at the University of Michigan, and I participated in some programs in Ann Arbor and Detroit. And so some of these lectures can be converted to a book. And I've already talked to publishers. So if you're interested, please let me know. The idea is to try to make math interesting and engaging, to give people an opportunity to think about things differently than they have before. This is actually one of the possible benefits of rethinking our educational system, is less rote memorization, less regurgitation of facts. I have never gotten a job because of the facts I know. I've gotten a job because I can talk to people. And how do you convince people? And that's going to be extremely important when we're looking at our statistics. So if anybody's interested in this, please let me know. Okay, so definitions. So as soon as you take a class, at least once you get to the high school level, you immediately start talking about what's my average, how am I doing relative to everyone else in the class. And so I'm assuming everybody has seen the concept of the mean. And to be a little bit fancy, we'll call it the arithmetic mean. So if I have 2 numbers, x and y, I define the mean as the number in between. So the mean of x and y would be x plus y over 2. So anybody have an idea why there is a symbol for Ohio State in the bottom left corner? You know the full name of that great institution of the Midwest? It is the Ohio State University. Not just Ohio State, it's the Ohio State. I wrote the average or mean is the number in between. There's many numbers in between. The is a bad word. There's more than one mean that we can define. And that will lead to different statistics. And again, I don't think these are going to be the statistics we're going to want to use when we talk to the state, but I want to use this as an opportunity to take a concept that most of you have seen numerous times. If I want to calculate my average, add the numbers and divide by 2. There's other ways of doing it. I just wanted to open you up to this questioning. So what properties would you like a mean to have? Now in mathematics, we always like to say, without loss of generality, I don't want to consider all the cases, I'm going to normalize things. Maybe I'm going to assume I have a triangle and the longest side is 1. Or I have a circle and it has radius of 1. I'm going to assume my 2 numbers are both positive, and I will make x to be at most y. Why do you think I have y larger than x? So why do I can do it either way. Any thoughts as to why I might make y larger than x?
it doesn't really matter. You can assume one way.
Correct, but why would I choose Y? Yes. It comes later in the alphabet, it's bigger. And if you don't like the number of letters we have, Dr. Seuss has a wonderful book on Beyond Z where he adds more letters to the alphabet. This way, when I quickly glance down, Y is the later letter, Y should be the bigger number, or at least as large as X. So can anybody tell me what properties you would like the mean of X and Y to have in this situation? That if your statistic doesn't return this value, your spider sense is tingling, you're saying, no, this can't be a good definition of mean.
Positive.
Positive. You know, we have two non-negative numbers, the mean should be positive. Great. Can you be stronger than positive? Any comments about its size?
It needs to be between X and Y.
It needs to be, okay, well, don't, so we're using the word between, okay. It's gotta be between X and Y. So if the mean is not between X and Y, I'm a little shocked. You know, I got 90 on the first exam, 85 on the second, and I got an average of 103.
Yeah.
Okay. Any other property you want, and the other property I'm thinking of is actually a special case. Can anybody give me a special case of X and Y where you should be able to calculate the mean very easily?
They're the same, it should be the same.
And so if X and Y are the same, the mean should just be that. So I'm going to call these the two properties I want. And really the second property I get immediately for free from the first because of X equals Y, they're forced to be together. All right. So the first question is, does the arithmetic mean satisfy these properties? Almost surely it does, or we wouldn't be studying it. And so the algebra isn't too bad. Just if 0 is less than X plus equal to Y, then if I add X over here, I get X plus X is less than X plus Y. And since X is less than Y, I can replace the X here with Y. And so as you just go through the algebra, you see, yes, it does work. Okay, not too surprising. If you check the second property, well, we actually get it for free, but it's not bad to just do it directly. X plus X over 2 simplifies to just X. So we're going to write AMXY for the arithmetic mean just to save space. Almost surely, there should be other choices of mean if I'm giving this one a name arithmetic mean. If there was only one mean, I could just call it mean. All right. So is there another choice of mean that satisfies our desired property? So you give me any X and Y, it's going to be something in between. And the mean of X and X is going to be X. So any thoughts on what might work? So you can assume a positive, and Y is at most, and Y is greater than or equal to X. Yes. So the geometric mean. So what is the geometric mean? Good, so instead of adding, we can multiply. So what should we do? The square root. So let's try the square root of X and Y. So let's just check on some numbers. This is not a proof, but let's build some intuition. Let's take the geometric mean to be the square root of the product. So the square root of 2 and 8 would be the square root of 16 is 4, and 4 is between 2 and 8. If we do 1 and 100, the square root of 100 is 10, and that is between 1 and 100. So at least the geometric mean is reasonable in these two cases. It's starting off right. How do you feel looking at this relative to the standard mean? Are you about to switch? Or does this give you some pause? Yeah. Okay, you have a, say it again? You don't trust this. Normally it's not until like the third week of the semester that students start distrusting me. Must be the mask. No, I can take it off.
It weights the lower number.
Yeah, the way things are weighted, you know, in the arithmetic mean, what's the arithmetic mean of 1 and 100? Approximately 50.5. But the geometric mean is 10. So I got a 1 on the first exam. I really bombed it. Realized I probably should have used a pen that actually wrote. Didn't realize I had a blank paper. And then the second one, I got everything right. And my average is 10. So it's something to consider as to, does this have good properties? So So we want to show that the geometric mean is a mean, that it really is always going to be in between. So the first thing is, we know x is less than or equal to y. So x times x is going to be less than or equal to x times y, and that's going to be less than or equal to y times y. So x squared is at most xy is at most y squared. So if we just take square roots, we get x is less than or equal to the square root of xy is less than or equal to y. So it does satisfy our first property. The second property is more straightforward. The geometric mean of x and x, it's just the square root of x squared, it's just x squared done. So we will call this the geometric mean. And now we have two notions of mean. So they both have good properties. They both satisfy our requirement. We are more used to the first. That doesn't mean the first is better. Does everybody know how to evaluate a polynomial? If I give you a polynomial of degree 6, and I want to figure what's its value at 2, how would you find its value at 2? You plug in 2 for everything. There's actually a much better way of doing that, far better. And the better way of doing this is the basis of one of the key ingredients in RSA encryption, which for years was the gold standard. Just because you're used to doing something one way does not mean that it's the best way. Similarly, just because a voice of authority says you should do something one way does not mean they're automatically right. Initially, all the guidelines on how to put people in classrooms was to use a square packet, a square lattice. If you are truly concerned about trying to get as many people as possible while maintaining a fixed separation, a hexagonal packing does better. And I actually brought this up in some school committee meetings, and I actually showed pictures of how many more people you could get. And there's sometimes structural reasons why you might not want to do that, but it's at least something that you should be aware of. And so just because somebody says that this is how it should be done, just because they're a voice of authority, that doesn't mean they're wrong, and it doesn't mean that they're right. So really think about it. Think about what are the justifications. So let's try a couple of examples. So if we take x equals 2 and y equals 8, the arithmetic mean is 5. The geometric mean is the square root of 16, which is 4. If we take 3 and 12, then the arithmetic mean is 7.5, and the geometric mean is going to be 6. Any thoughts on what you see? Any conjectures you want to make? So the arithmetic mean is greater than the geometric mean.
Or equal.
Or equal. Excellent. Because if I take x to be y, then they have to be the same. So the arithmetic mean is at least as large as the geometric mean. Why do you think I chose these numbers? Yeah, they have nice square roots, right? So you always want to think about what data is someone giving you. I'm choosing these numbers just so that I can do nice calculations. I love to look at extreme cases. And when you look at extreme cases, you can often get a better sense of how things are going. Let's push things to the limit and see what's going to happen. So can you give me any extreme cases for x and y? Okay, good. So what if y is going off to 1,000,000? And so let's try x equals 1 and y is very large. So if I do that, the arithmetic mean of 1 and y, oh wait, did I remember to record? I'll edit that up later. All right, so the arithmetic mean of 1 and y is going to just be 1 plus y over 2. If y is really large, it's y halves. So if y is 1,000,000, the arithmetic mean is essentially 500,000. But the geometric mean is going to be the product of 1 and y square root of y. That's much smaller. The square root of 1,000,000 is about 1,000. So as y gets very, very large, the arithmetic mean dwarfs the geometric mean. You could also do the other case. If y is very small, now I'm being a little bit bad here because I always say x is supposed to be smaller than y. If I keep one of them at 1 and make the other one very small, it will also work out as well. I'll just leave that as a calculation that you can look at. So we would conjecture that there is a relationship, and it has been said that the geometric mean is less than or equal to the arithmetic mean. This is one of the most important inequalities in all of mathematics, this relationship between the geometric mean and the arithmetic mean. It is derived from an even more important inequality, If you have a real number and you square it, it's not negative. So any real number squared, the lowest it can be is 0. And so what you do now is you look at the square of the square root of x minus the square root of y. So whenever you see a math proof, there's always this, why did they think to do this? It's very easy as a professor to just go through lines of algebra line by line by line and give you the justification. And completely skip, why did anybody ever think of arguing like this? Well, the argument is we want to somehow get a square root of x and y. If I have it like this and I square it, well, if I use FOIL, a minus b squared, it's a minus b times a minus b. It's aa minus ab minus ba plus bb. Over here, I'm going to get square root of x times square root of y. That's going to be my square root of xy term, which is what I want to get. And then over here, the a squared is going to become root x times root x. Oh, that's going to just be my x. So this was chosen because things are going to go out nice. So when we expand it out, we get 0 is less equal to square root of x squared minus 2 square root of x square root of y plus square root of y squared. So 0 is less equal to x minus 2 root xy plus y. So we bring the 2 square roots of y to the other side. We get 2 square root of xy is less equal to x plus y. So the square root of xy is less equal to x plus y over 2. And there's the geometric mean and the arithmetic mean. There's lots of other proofs you can give. You can generalize it. But this is a great start. Any questions on what we've done so far? We now have a way of comparing the two statistics. And we can say if we calculate means one way, this is going to give us higher means than the other way. And it's good to be aware of what kind of consequences will your choice of statistics have. All right. So let's try to generalize this a little bit. So I know some people have heard of the geometric mean. What if we had 3 objects, and of course the third one has to be z, right? The arithmetic mean, we could probably say, well, let's just have it as x plus y plus z over 3. We might generalize the geometric mean by saying, well, let's take the product, and before we took the square root because we had 2 things, let's take the cube root because we have 3 things. And now if we take x equals y equals z, this new geometric mean will actually just give us back x. So it's good. And you can show that it satisfies all the properties. But what I want to do now is to show, hopefully, a statistic that no one in this class has seen before. Let's look at xy plus yz plus xz divided by something and raised to some power. Could we make this into a mean? So has anybody seen anything like this before? Excellent. Anybody know why I'm choosing xy, yz, and xz? Where's that coming from? Any thoughts?
It's like a symmetric sum.
Yeah, it's a symmetric sum. Look at all the ways I can choose 2 out of the 3. I can do x and y, I can do y and z, I can do x and z. So can we find a choice of a and b so that if we divide by a and we raise it to the b, that it's going to satisfy x less than equal to triple mean less than equal to z, and the triple mean of xxx equals x. So what would be a good choice of x, y, and z to build some intuition? Any thoughts on what we should try for x, y, and z?
Well, in the case where really a equals to
Okay, good. So you're saying let's try x equals y equals z equals x. So when we do that, we then get x squared plus x squared plus x squared, or 3x squared divided by a to b equals x. And this has to be true for all values of x. So what does a have to be? Has to be 3. Has to cancel that 3. And then b has to be 3 halves. And so we actually now have a guess. By just looking at that one case, we have a guess that if we take, do I have a typo here? No, b equals 100, and a equals 3. So when we plug this in, it actually works at least for the triple mean of 345. It returns 3.958. What's the arithmetic mean of 345? 4. They tried to choose nice numbers. So the triple mean is less than the arithmetic mean. And you can start asking, what are the relationships between all of these different quantities? And so just some quick final thoughts about this before we now shift to COVID data. So we had a relationship between the arithmetic mean and the geometric mean. If you remember the logarithm function, the log of a product is the sum of the logs. The log of xy is the log of x plus the log of y. So if you think about it, if you apply logarithms to the geometric mean, you actually get the arithmetic mean of the logarithms of the data. And a lot of times we look at logarithms of quantities. And so this is just something to be aware of. So for the 300 level people, I'm going to be assigning you some homework related to extensions of this. Do not read the paper that's linked here until you finish the assignment. It turns out there's a whole slew of additional inequalities inspired by this. So this ends the theoretical part of the lecture, just trying to develop this concept of what is a good statistic, what properties do we want a statistic to have, and once we make those decisions, what are the consequences? But the key thing here is that we have a choice. There is more than one notion of a mean that returns a number between x and y. And you want to think, what is the right one for what you're doing? Any baseball fans here? Anybody ever read Moneyball by Michael Lewis?
Yeah.
If there was a textbook for this class, it would have probably been Moneyball by Michael Lewis, where it's about the Oakland A's and how for years they actually listened to a lot of the stats people before other teams did about which statistics really mattered. And a lot of people were putting an emphasis on the wrong statistics. And they realized that they could take advantage of teams. Oh, you want my star closer? Oh, I hate to trade my star closer, but I do happen to need a second baseman, so. And they could inflate certain people, make people look better and more desirable for trades. After a while, it starts getting harder and harder to do that. But it's, can you find the right metric? And this is all about trying to find the right metric. All right, so here is a picture of the Commonwealth of Massachusetts. So our county is in yellow. It's listing as 1.5 cases per 100,000 in Berkshire County. Anybody know roughly the population of Berkshire County? Yes. You're within a factor of 3.
80,000.
80,000, you're within a factor of 2. Wait, actually wait. This is a great opportunity. So let me, okay. I just want to hide something, okay. So this is great. So we have, can people see this on the screen? First guess was 320,000? Oh, you said 120? Oh, I thought you said 320. Oh, can I use 320?
Sure.
All right, I'll use 320. Oh, this is not going to be as good then. Then you had 80,000. So if those are our two guesses, the arithmetic mean would be G plus H divided by 2. And then the geometric mean would be the square root of GH. And so you get 200,000 and get 160,000. Which do you think is closer to the true population of Berkshire County?
160?
160. The actual answer is 125,000 roughly, I believe. So your guess of 120,000 was actually extremely good. But it's an interesting question in terms of if you have a lot of guesses and people may not have much of an idea, which do you think is actually going to give a better prediction? The geometric mean or the arithmetic mean? The arithmetic mean can be more sensitive to one really large or really bad value. Okay, so let's go back to sharing. Okay, so here's Berkshire County, here's the rest of the Commonwealth of Massachusetts. And going forward a slide, so here is the Massachusetts COVID chart. And it's based on the average daily cases per 100,000 residents. What's nice is basically Berkshire County could be figured as 1 unit. Okay, it's 125, not 100,000, but basically great. And there's 4 designations. The red is the highest risk, the moderate risk is yellow, lower risk is green, and then communities with fewer than 5 cases are not given a designation. And what we're talking about is the number of cases per day calculated with a 2-week rolling average. Or a 2-week average, I'm not sure if they keep rolling. What's the advantage of doing an average over 2 weeks? Okay, why? You said asymptomatic cases show up? No, that's. Yeah, so when you have a small number of cases, 1 or 2 days that are a little bit off, you also don't want to have your system maybe so sensitive that 1 day observation completely changes you. Or maybe you do. Maybe the disease is so deadly and spreads so quickly, we have to shut things down immediately. That we can't afford to wait for a 2-week average. You can make almost any case. The question is, how compelling of a case can you make? What are the consequences going to be? So what do you think the big question is? When you look at this, what would you like to know?
Trends.
I'm sorry?
How's it trending?
Okay, so one question is, how is it trending? Are towns moving in a certain direction? But so the categories are red, yellow, green, or gray. Gray, I've told you, is communities with fewer than 5 cases. Yes? What do red, green, and yellow mean? Anybody have any guesses as to what it would mean to make you yellow? Yes? Okay, so more than 1 case per 100,000. So if you have just 1 case per 100,000, do you think that's enough to make you yellow? Or do you think you need a little bit more? And this is averaging 1 new case per day for 2 weeks. So in Berkshire County, that would mean essentially 1 case a day for 14 days. And Berkshire County should be yellow. But of course, communities with fewer than 5 cases are not given a designation. And so the other map I showed you, Berkshire County was yellow at 1.5 cases on average per day. Yes?
Good question. Do they take into account geographical area?
No. They do not take into account geographical area. So here is the legend. It's the average daily case rate per 100,000. So gray is less than 5 reported cases. Green is less than 4 cases per 100,000. Yellow is 4 to 8 cases per 100,000. And red is more than 8 cases per 100,000.
I have one quick question.
Yes.
For the 100K cases, is it that reported, or is that just like population?
It's, I believe, population. So they look at how many cases are reported, and they look at your population. So the big question is, what is it going to take to move Williamstown into different categories? So what would it take to move Williamstown from gray to green to yellow to red? So the population, I looked it up in 2019, the last year I could find, the population is, I love this, about 7,759. Probably a little bit different now, but about. This does include students. So you are included in the number of people in the town, even if you are technically living someplace else. We are counting you as our population. So we're going to now derive the correct formula. If we have C cases in a 2-week period, what is the average number per day per 100,000 people? So take a moment and try to think how you would write down a formula for this. I tell you, we observe C cases in a 2-week period, and I want you to tell me what would be the average number of cases per day per 100,000 people. What would be your formula? Pause the recording. Anybody want to give me some thoughts about what the formula might be?
100,000 divided by 7,759 times G equals
Okay. I have an extra factor of 14.
that's the per day.
Right, so A is the per day. So this is where you have to be very careful about watching units. And I put them in a different order. I multiplied them in the other, it doesn't really matter. So basically what I'm doing is, if I have C cases in a 14-day period, this is my daily average, and I'm dividing by the number of people. And then I'm just scaling it up. So imagine now I had 100,000 people, how much would that be? So that they would be the same fraction. And so I just solve for A, and I get C over 14 times 100,000 over 7759. So any thoughts about how many cases we need in a 2-week period to move Williamstown from gray to green, from green to yellow, and from yellow to red? So without doing the algebra, yeah.
You said A equals whatever the number of cases A and solve.
Good. So you could set A in and you could solve for C perfect. But do you have any thoughts about just looking at this? Does C need to be on the order of 100? Does it need to be on the order of 10? Does it need to be on the order of 1? Can you give me an order of magnitude?
0.
I'm sorry?
It has to be around 4 or 5 cases.
So here is the scary data. Williamstown can never be green. If there are 4 cases, A is 3.68, and according to the state metric, if there's less than 5 reported cases, then you're gray. If C goes up to 5 cases in a 14-day period, the average goes up to 4.6. And that's enough for yellow. So Williamstown will never pass through green. If C equals 8, A is equal to 7.36. If C is equal to 9, A is equal to 8.29. So if we have 9 cases in a 2-week period, we've moved to red. I do not believe the state, well here. Can somebody tell me good things about this metric and somebody tell me bad things about this metric?
Couldn't it change if someone moved to Williamstown or left?
I'm sorry, say that again?
Couldn't it change? Couldn't the metric change if Williamstown lost residents
If Williamstown lost?
or gained residents, like if the population?
Yes, so if the community gains or loses residents, the metrics can change. The only time that would happen is when most of the college students are sent home. And that would be a significant population change. Small shifts in population should not really affect things that much. I do know a lot of people left New York City, and if they had houses in other parts of the country, during the pandemic, they left New York City and moved to other places. And so, the question is, do you have enough movement to be, a significant change in the population? Definitely, when the college students went home, there was a hit of around, 1,600 to 2,000.
Mic check.
Any other thoughts about this metric as to what might be good or what might be bad?
Oops. I think it's bad for small counties.
Why is it bad for small towns?
Or small towns, because the 100K is divided by a very small number. So like it's not one unit. Like the 100K is too big of a unit for Williamstown, for example.
Okay, so I'm going to try to paraphrase a little bit. Basically, one more reported case has a tremendous impact when you're a small town. New Ashford is one of the communities near us, and they send their kids to the Mount Greylock Regional School, which is where I serve on the school committee. It's Williamstown and Lanesboro. A few weeks ago, there was a scare because there was a 10% positive test rate of people in New Ashford. Does that scare you, that 10% of people were testing positive? Okay, why doesn't that scare you? Yeah, anybody want to guess how many people were tested that day? 10. And one person tested positive. So yes, it's a 10% rate, but when you have that few tests, What is happening in Williamstown right now? A lot of tests. Are you more or less likely to find people with COVID if you test? You're more likely. So these state metrics have nothing. I'm sorry, I'm supposed to come. And I promised I would actually do this. I'm going to turn on the video for a second. So my daughter made this beautiful rock for me. It says, I love you on one side, and it says, Dad with a heart on the other, for me to hold when I start trying to lose my temper about some things, and to remember what this is all for. I will not tell you how often I have held this at some meetings. It's good that some meetings are by Zoom. The metrics do not take into account how many tests are done. The more people you test, the more likely you are to find people who test positive. This is one of many, many issues with this metric. The metric has some good things about it. But when you have very small populations, now I do not know if this is true. I have heard, and I need to get this confirmed, that if you test positive, you are not tested again for 90 days. And if that is the case, then if there's a false positive, that could have a huge impact in statistics like this. And again, in general, you don't worry about a false positive if you have very few tests going on. But when you have a tremendous number of tests, and again, I don't know all the detail. I've heard that the Broad Institute's test looks for, do you have a certain count level of things? I'm not positive. But if this is the case, you can choose a high threshold for when the test is going to be positive, or a low threshold in terms of, do you have enough to be considered a positive case? If this is how it's being done, and you have a low threshold, this is not necessarily a bad thing. Why would you want to have a low threshold? For telling somebody that they're positive? Yes? Good, good. So if you have a low threshold and we're really trying to clamp down on the spread of the disease, a low threshold will stop people from going out. You'll quarantine them. What would you like to do, though, with somebody who tests positive? So if somebody has a positive result, what would you do?
Test them again.
Test them again. But we may not be able to test them again. If that's the case, I have some questions about why we would want a situation. And again, I don't know if this is true. I just heard this yesterday. It'll be interesting to see if that's the case. But if you have a low threshold, you are more likely to catch people and not send them out, which is great in terms of stopping the disease. And the cost of having some people just do a little bit of extra quarantining relative to the spread of the disease, that might be a really good trade-off. If you have a high threshold, then you can be very confident when you get that test result, but you might miss a lot of people who can spread. This is why you often have your cheap tests and more expensive tests. Your tests that are maybe fast to do, but maybe they err a little bit and are maybe a little bit more likely to say you're positive when you're not. Is it better to tell somebody that they're positive than they're not, or to tell somebody that they're negative and they're not? Which way do you want to make your error? Yeah, you would much rather tell someone that they're positive and not than to say that they're negative and not, and then they go out and spread things. Has anybody ever been in an elevator? What's the first thing you read when you get into the elevator?
Capacity.
Capacity. I was wondering, says, well, I normally bring a book or, yeah. You normally look at the capacity and you look around you and you say, is this a safe elevator to be in? Yeah, almost sure.
Mm-hmm.
When they write the capacity for the elevator, the way they actually do this is they put some people in the elevator and they keep putting more and more people, and then the elevator crashes down eventually, and then they just weigh the mass on the, no, okay, that's not how they do elevator testing. Do you believe that the capacity of the elevator is 2,000 pounds, a nice round number? What do you think it is? A little bit more, right? How much higher? How much of a safety factor have they built in? Same thing for bridges and whatnot. You want to be a little bit below that so that you have some margin of error. You don't want to be like, uh-oh, he had a double ice cream earlier today. That's just enough to push him over, and it's so sensitive. So you want to think which way you want things to go for your statistics. It is much better to have a few more false positives. But this metric is, I think, not as good as we can make it. I'm trying to be extremely diplomatic in my phrasing. The state has already changed its metric once. And so right now in the agreement we just signed yesterday, metric CID says under the state's new community COVID ranking model, if we have a ranking of yellow or red in either of the member towns of Lanesboro or Williamstown for 3 consecutive weeks, then we will automatically move to remote. The state guideline is that we should be either remote or hybrid. If it's red, it should be remote. The state says if you're yellow for 3 weeks, be either remote or hybrid. We have elected to be just remote. Here is an interesting calculation that I did, and I mentioned this at the school committee last night. If 5 people test positive in week 1, none in week 2, 5 in week 3, and none in week 4, that's 10 people in a 4-week period. The 5 over here is enough for the first 2 weeks to be considered yellow. And the 5 here is enough for the next 2 weeks to be considered yellow. So 10 people in a 4-week period is enough to move the school into fully remote. And when you consider the number of tests being done by Williams College, and again, it is quite likely that if you're getting a lot of positive tests, you might want to be remote. But the question is, do you want it to be a mandatory, or do you want it to be a decision using local data and trying to understand, well, what are these 5 cases? If it's one family that's all self-contained, if it's people in a long-term care facility, if it's students who have just returned to the college and are quarantined, that's very different than if it's teachers and kids. And if it's teachers and kids, completely different story. So the assignment, and for those of you who are interested, and your alums, you're welcome to it. If any of you have Charlie Baker or Commissioner Riley on your speed dial, please let me know. The job is going to be come up with a better metric. And this is something that will have an impact, not just locally here, but throughout the Commonwealth of Massachusetts. They've already changed it. Originally, it was just if it was yellow, you do these things. Now they've said, wait until you get 3 straight weeks of reports. But things are so sensitive right now that 10 people in a 4-week period can shut down the schools. And so one of the things I really want to do with this class is give you an opportunity to see math in action. This is not advanced mathematics. That doesn't mean it's not good mathematics or math worth doing. You need to be able to explain things to people. And you can all imagine just how much fun it would be to give a math lecture, to the General Court of Massachusetts and trying to explain what you're doing. There are trade-offs. Sometimes it's better to have a metric that might not be as good, but is easier to explain and seems reasonable and people can understand and buy into. You can also have the more complicated formulas. Any football fans here? Okay, can you define the quarterback ranking? Rating. There's a formula for the quarterback rating. It's super complicated. It's easy for the computer to crunch it out, but it's normalized. If I give you a quarterback rating of 105, good quarterback, bad quarterback. Pretty good. Quarterback rating of 60, not so good. My favorite was years ago, the Jets were playing and their quarterback threw 8 passes. 2 were caught by Jets, 3 were caught by Bills. If you viewed him as playing for the other team, he actually had a higher rating. So it takes into account interceptions, completions, touchdowns, lots of different things. It's hard to do on the fly, but for something like this, you want a better statistic than something you're just doing with your fingers. So these are just various things to balance. So I will send you more details about this, but if this is something that interests you, let me know. Friday is going to be our first guest lecture. We're going to have somebody from, I believe, an energy company who's going to talk about what is it like to run a business in the time of COVID. And then I will send more details later about what the next few classes are going to be. There's been some fluctuations in terms of people adding the class, and so I wanted to just give everybody a chance to get it. Right. Any questions before we end for the day? All right, have a good day.
Any reasons for that choice of